To you, because the way the equations for this are written are very different than what you've seen prior. The notes that you took from the summer math video that I asked you to watch are also going to be of importance in this chapter again, because we're going to be dealing with some new vector math that you've not done before. And I don't believe they cover it in any of the AP calculus courses because it's generally part of a separate math class on vector algebra. Which, if you're going into any STEM field, you'll be taking a one semester course on it. Usually it's part of the science school and not the math school. I don't know why, but that's where it is. So anyway, we're going to talk about work and energy. And probably the most important thing I'm going to tell you for this chapter and the next one. When you're solving problems, you may think of a way to do it using kinematics. That's not going to be allowed. Okay. So none of the kinematics equations can be used in this chapter and the next one while we're working in these two chapters. Once you go to take the AP exam, you can do it whichever way you want. Okay, there may be a way to do it using energy. There may be a way to do it using kinematics. But while we are in these two chapters, when you take your test and you're doing your homework, you should not be using kinematics. None of the kinematics equations can be used here. Okay, because what's the point of these two chapters? Work and energy. You need to understand these concepts and this problem-solving approach, not using anything we did in chapters 2 or 3, in other words, okay? Forces are still allowed. We still use forces to, but we don't use kinematics to do it. So the equation D is VIT plus 1/2 AT squared, can't use it. Can't use A as change in V over T. Can't use it. Can't use VF squared equals VI squared plus 2AD, or V bar is VI plus VF over 2. Can't use any of them, all right? So let's talk about work and energy then, and what you should be doing in this chapter. Remember that work is done whenever a force is pushing an object in such a way that it moves somewhat parallel. What's up, Evan? Okay. So work, the general definition of work, is what is accomplished when a force moves something through some distance, which happens to be parallel to the way it was pushed. So I take this folder and I push it. I'm holding it here. I'm going to walk this way. Am I doing any work on this right now? No, why not? I sure am moving. I'm pushing it in a way which is perpendicular to the way it's moving. I'm pushing it up, it's moving horizontally. The only time work is done by a force, and we talked to you about this in Regents Physics, is when that force is pushing in some way which is going to have a component parallel to the way it moves or to the way it's displaced, okay? So that's really important to understand. That was the basic concept from the Regents course. And remember that whenever work is done, some kind of energy gets transferred. And there's two types of energy that we'll be dealing with at this point, kinetic and potential. And you know what those two types of energy are. And again, here's that note. You may not use any kinematics concepts to help you solve these problems in these two chapters. So when you take your chapter test at the end of chapter 7, because 6 and 7 are tested together, if you use a kinematics approach, it's not going to receive any credit. I'm just putting that out there right now, because this is on work and energy. You have to show me you can do this with work and energy. All right. Okay, so let's get into the new stuff or review of old stuff. So we're going to start off by talking about what you did in Regents. And that's pretty much just this one slide. Dealing with anything that has a constant force being applied to it as it moves in one dimension, horizontally, vertically, whatever, only in one direction. And what we learned in Regents physics is that work is the product of the force and the displacement. It's not wrong, but it's very limited. This only works when the force that you are applying to the object doesn't change. And that rarely happens in the real world. When you apply a force to something, the amount of force changes over time or with position. So this is why I say it's limited. Remember that if the force and displacement are in different directions, you need to consider only the component of the force that creates the displacement, which means that in this particular situation, which was a situation we did show you last year, I have a box, I'm pulling up and right. That box moves to the right through that displacement of delta x. Only the horizontal component of that force would do any work. And why? Because that is the component which is parallel to the delta x vector. Okay. So the way we would find that work by that force F, if it's constant, we would take just the horizontal component of it, F cosine of theta, and then multiply it by the delta x. And that's what you learned how to do last year. Okay. Most of the time last year, however, the force was always in the same exact direction it was moving. So you didn't even have to worry about the cosine of the angle in there to give you the component. You just said, oh, it's FD. Done. That only works if F is constant in magnitude and D is parallel to F. When you have a component like this, you have to introduce the cosine in there. All right, so let's get into the newer stuff. So work, this is still old stuff. Work is capital W, abbreviated, joules, abbreviated with capital J. It's a derived unit, which is a Newton meter. A Newton meter is the same thing as a kilogram times a meter squared per second squared. So it is a derived unit, and it's a scalar, so you won't say it's going north, south, east, or west, or any of that kind of stuff. However, it can be positive or negative, and you did see that in the Regents course. Let's talk about when work is positive, what that means, and when work is negative, what that means. It really goes back to the idea that when you do work on something, it's transferring energy. So if the work done is a positive amount, it's not telling you that you did work to the east or you did work to the north. That would be direction. It's telling you what happened to the energy of the object. Think of changes in energy. So a positive amount of work done indicates that the energy on the object gained energy by that work being done. Think of it as an energy increase. Positive changes are increases. So positive work indicates energy is gained. Negative work, therefore, would mean what? Energy is lost, okay? Or the energy of the object is decreasing. That work was decreasing the energy that the object has. That's a really important concept, which will then translate into our next chapter 7 when we get there, when we start to deal with conservation of energy with work being done. So let's now talk about the total work done on a particle. First of all, what do we mean by a particle? We discussed this when we talked about projectile motion. We're dealing with objects that are perfectly rigid, non-rotating, which means that all of the parts of this object have identical displacements. So that would mean if I wanted to find the total work being done on an object where there are multiple forces being exerted on that object, most situations we have multiple forces exerted on something, then what we have to do is look at the algebraic sum of each amount of work done by each individual force. Find the work done by force 1, find the work done by force 2, the work done by force 3, so on and so forth, add them all up. And that gives you the total work. Or you can remember that when you have multiple forces exerted on an object, it's really only the net force that's of importance. So figure out what the net force is. And then the work done by that net force would be the total work. Okay. All right, let's now talk about kinetic energy. Again, a little bit of review. It's energy associated with motion. Right now, we're going to deal with just linear speeds, non-rotating things. Once we get to chapters 9 and 10, we'll have objects that are rotating as well. So there's a different form of kinetic energy we'll describe. Now, here's something new. Instead of writing this as KE, And I really want you to change your thinking on this. We don't write KE anymore. We just write K. Look at your reference table. You will see that it talks about capital K, not KE. You will not see KE anywhere on there. It's just K. Do you see it? And it tells you the equation for kinetic energy, capital K, which of course is measured in joules, is 1/2 mv squared. That's not anything new. We learned that last year. Where V is not a velocity, nothing here is in bold, so it's not a vector. It's everything is a scalar. So V represents the speed of the object. And mass, of course, is kilograms, also a scalar. All right, let's now talk about the work kinetic energy theorem. This comes from Newton's second law. Remember, Newton's second law says that a net force causes an object to accelerate. So when you're accelerating, that means your velocity changes, which means that you're going to have a change in your kinetic energy. So that would mean, therefore, that the total work that's done, which is the work done by the net force, is going to cause a change in your kinetic energy. This is the work energy theorem, or the work kinetic energy theorem. We did introduce this to you last year, but a lot of students had difficulty with this. Unfortunately, you got to get over that difficulty this year because it's an integral part of this course and this curriculum. That the total work done, which is the work done by the net force on an object, will always cause a change in the kinetic energy of the object. Not any kind of energy, specifically the kinetic energy of the object, which means we would take the final kinetic energy and subtract the initial kinetic energy to give us the total work that's done. Now, here's where things get fun, and we start to think about calculus. Now we're going to have forces that change in magnitude and direction possibly. So the amount of force that's being exerted on an object can be variable in size. When that happens, often what we will do is we will make a graph of the force versus the position of the object, like what you see here. We're introducing this where you can still see that in this case, the force is a constant amount. From position 1 to position 2, the force remained this constant amount. And if I wanted to know how much work was done by that force, and all I had was the graph, what I could do graphically is calculate this area between the force and the position change. Okay, so graphically, work is equal to the area on a force position graph, not a force time graph. That's very important. Probably the most common mistake I'm going to see on your next test is when I give you a graph, you're going to say that you need time. You're going to do stuff with force and time. Force and time has to do with impulse and momentum changes. If you remember, F net times delta t, or F net t was an impulse. This is F times a displacement, a force and a position on the graph for work. Force and position, or change in position. Now, let's start to think calculus. What is an area analogous to in calculus? An integral. That's exactly right. So let's say I have a force function that is not linear. Finding the area under that curve between the curve and the horizontal position axis is going to be a real pain in the you know what. Because it's curved, right? You can't calculate the area with a curve. You're going to get an approximation at best because you're going to be missing pieces of area or having too much because you go above the curve. So what we do instead when that force changes over time is we're going to use an integral to find that area. Or I should say not the force changing over time, force changing over position. So the work, and I'm not sure if this is written on your reference table or not, work is equal to the integral of the force with respect to the position. Now, in your text, at least in this section of the chapter, they write F sub x dx. What this is trying to tell you is that, again, we need the component of the force in the same direction as the position function. So that way you have to have parallel components. That's what they're talking about again. So this would be a force along the x-axis producing a change in position along the x-axis. Now notice that the limits of the integral are positions, they're not times. When the variable that's involved in the integral is position, the limits of the integral have to be positions as well, not time. So like I said, that's probably the most common mistake I see with this calculus, is that students want to find work by doing an integral of force with time and then put time 1 and time 2 there. And that's not work, that's an impulse. We're going to learn about that in our next chapter 8, after we finish this work energy stuff. All right, so we're looking at the integral of the force with respect to position from one position to another. All right, this brings us to the vector math stuff called a dot product. You may recall from the video I asked you to watch over the summer. It's still linked in the AP Summer Classroom if you didn't get a chance to see it, or you may want to go back and review it again to talk about dot products. Dot products are what we get when I'm taking two vectors and multiplying them. There's actually two different things you can get when you multiply two vectors together. If you multiply two vectors together, you can either get a scalar result that doesn't include a direction, which is what we're going to do here, or you can multiply them together to give you another vector, which is what we're going to learn about in a future chapter. That's called a cross product. Dot products are involved whenever I need a scalar result. And whenever I need a scalar result, like with work, right, I'm multiplying a force by a displacement. Force and displacement are both vectors. There's got to be something true about those two vectors in order to give me a scalar result. They have to have components in the same direction. So what we learned, and we saw this on a previous slide, even though I didn't kind of hit it home, I'm trying to hit it home right now, is that when you're doing or trying to find the work done by force F, notice this is in bold. We use bold, remember, we mentioned this in an earlier chapter. Things in bold in the text indicate it's a vector. It's a vector. And you see how DS here in bold, that means that's a vector as well. I'm multiplying two vectors, but I want a scalar. We already know that work is a scalar result, and something has to be true about those two vectors I'm multiplying in order to get an answer. They have to have parallel components. And we showed you how to get that cosine of theta in there to give us the component of F in the direction of the displacement. That's called a dot product when we get the scalar result. So what that's going to look like, and you should have seen this in the text, is something that looks like this. This is a generic formula to calculate the dot product of two vectors A and B. And this is not the only time in this course that we'll be doing dot products. You take other STEM-related courses, you're going to be doing a lot of dot products and a lot of cross products. That's why you'll take another course when you go to college on just vector math or vector algebra. Here I only have two vectors. I could put 3 vectors in there. I could put 10 vectors in there. And then you're dealing with these very complicated matrices. And your graphing calculator starts to actually do some real computational stuff. What you're seeing here, vector A, and the way we read this, we don't say A is multiplied by B. That word multiply goes out the window. What we say now, it's A dotted with B. A dot B is the way you read that. The dot stands for this thing called a dot product. And I specifically need to see that dot between the two vector quantities. Okay, don't put an X. You may remember from the summer video, that stands for something called a cross product, which is a different type of vector math. All right, you put a dot when you have two vectors. If I have two scalars, I don't care what you put between them. Okay, you're multiplying. Here, we're doing a particular type of multiplication called a dot product. So we have to use a dot between them. Without it, I don't know what you're doing. That's why I specifically have to see it. How do you find the dot product result? You take the magnitude of vector A, see it's not bolded, that means magnitude, times the magnitude of vector B, and you multiply it by the cosine of the angle between these two vectors, where that theta represents the angle between vector A and B. So what this means is that there's some properties of dot products we need to understand. And this table comes from table 6.1 in your textbook. It's on page 162. So when you're doing the dot product homework for think it's due the Tuesday before Thanksgiving. If not, it's due the Monday right after. It tells us, therefore, that if A and B are perpendicular to each other, that would mean the angle involved between them is 90 degrees. Cosine of 90 degrees is 0. So your dot product of A and B are 0. 162. Then if A and B are parallel to each other, what's the angle between them? 0. Cosine of 0 degrees is 1. So that means I just take the magnitude of A and multiply it with B. If the dot product of A and B are 0, it means one of three things could be true. It means either the magnitude of A is 0, the magnitude of B is 0, or they're perpendicular to each other. We don't know which. Okay, it could be any of those three. And then we're giving you some other properties. Notice if I take the dot product of a vector with itself, of course, that's just the magnitude of the vector squared. They're parallel to each other. Notice a dot product is commutative. Cross products are not. You'll see that later in the course. And then the distributive property also works. So remember that when we deal with vectors, we often write them in IJK notation, right? Remember that with the components? That's coming back here as well. So what we can see is that if I have a vector I, the unit vector I, dotted with itself, I get the number 1, because what is the magnitude of the unit vector I? It's a unit vector, has a length of 1. 1 times 1 is 1. They're parallel. But I dotted with J, they both have magnitudes of 1, but I and J, I points right, J points up, they're perpendicular. So that dot product result has to be 0. Does that make sense? Okay. So now, let's say I have vector A dotted with vector B, but both A and B are written with their IJK components. See that? When I do the distributive property, obviously I'm going to have AXI dotted with BXI plus AXI dotted with BYJ, and so on and so forth. But notice that I can reduce that down to just this. Why can I ignore AX in the I dotted with BY in the J direction? Why can I ignore those two and I don't see it here in the final result? Right? Yeah, because the I dotted with the J is 0. So I don't have to worry about any components distributing them to anything that's perpendicular to it, because that will reduce out to 0. Right? I dotted with J is 0. I dotted with K is 0. The only things that will matter are things that are parallel and in the same direction, both in the I, both in the J, both in the Z. And then, of course, because this is scalars, we just add those products. Because when you do the distributive, right, you got the plus signs in there, so that's why we're able to add them, giving us a net result. Likewise, I think this is called the chain rule, I think, in calculus with the derivatives. You can apply basically the distributive property here with the derivative function of A dotted with B. All right, so this is just basically review. If I'm using the dot product notation, it means that incremental work, dW, is equal to the force vector dotted with the incremental displacement vector. And that would mean, therefore, that the work is equal to the integral of the force with respect to the position vector. We already saw this, but instead of S as our general position vector, we used X, assuming it was along the X-axis. Could be along any axis. That's why they're using a general S right now. And that's from position 1 to position 2, not times. There's no time involved with this. It's all position. The only time gets involved is when we start to look at rates at which work is done. Time rates. And we learned in Regents physics that the rate at which we do work is called power. It's also the rate at which we move energy from one system to another. So power is still capital P, still in watts. That hasn't changed from the Regents course. But remember, whenever we do a rate, a rate is a derivative. It's a time derivative. So if I were to take the time derivative of our work function, that would give us our power. Last year, we didn't do derivatives. We just did deltas. Deltas are derivatives, changes, the change in work over time. Here, it's the derivative of the work over time. Or that other equation still works. We did do forces. Then we said multiplied by velocities, again, assuming they were parallel. Here now we know more specifically it's a dot product of the force vector with the velocity vector. Okay, and I think these may be on your reference table as well. You should be checking it out to see what's there. And if it's not, then thinking about, okay, future cheat sheet, I'm going to need these things to help me do problems. This is, I don't know why I even have this here. It's the same thing that we've already seen. All right, let's now talk about potential energy. Potential energy, remember, is stored energy in a system. This one's really a big change. We're not writing PE. And we can't write P because P is what? Power. So we use a U. You'll see, I think you'll see in a minute when you look at the graphs of potential energy why we're going to use a U. Number one, we don't use it for anything else. But number two, because it looks like the graphs that we see. Okay, so you'll see on your reference table U for potential energy. Still in joules. And there's two kinds generally that we're dealing with, at least at this point, gravitational potential and elastic potential. So gravitational potential is when you're dealing with masses separated by a distance in some type of gravitational field. And elastic potential energy, of course, deals with things that can stretch or compress, most often with springs. So we touched on this last year in Regents, and we said, don't worry about it. Unfortunately, we have to worry about it now. Okay. Conservative versus non-conservative forces. There's a lot involved with this in terms of understanding work and energy conservation and energy transfer. So what do we mean by a conservative force? And this is that's a statement that's directly out of your textbook. I have a CD with all the boxed things in your text. I copied them. I just took the image, placed it on my slide, took the image, placed it on the slide. It's right in your textbook. The definition of what a conservative force is. A conservative force, a force, you could tell if a force is conservative if the total work that force does on a particle, as that particle moves around a closed path means it starts in one spot, moves wherever, and goes back to its starting point. That's a closed path. If that work done by that force is zero. So I start here. I push it so it moves in all these weird directions. I get back to where I started. If the total work done by that force is zero, that force is a conservative force. What that would mean, therefore, is that it doesn't matter how that object moves if the force is conservative. It only depends on where it starts and where it ends. What it happens in between doesn't matter. Okay, so it's independent of the path. Examples of two forces that we can think of that are most commonly associated with being conservative are gravitational forces and spring forces, if the spring is ideal. If the spring is not ideal, most of us know the springs we work with are not ideal because we can create some thermal energy as the spring gets stretched or compressed. The molecules in the spring heat up. They start moving faster. So that would not be a conservative type of force. But if the force is ideal, doesn't heat up when you stretch it or compress it, and it always goes back to its original length, then that force on the spring would be conservative. The best example I can give you of something that is non-conservative is friction. And the reason for that is because if I take an object and I move it across a surface which has friction, and I want to get it back to its starting point, it is going to depend on how far it moved along the entire path. Shorter distances from start to finish points will have less thermal energy being created, and therefore friction is non-conservative. All right, so now let's look at how we would find a potential energy function. related to work. Hold on a minute. Look at this equation for a minute here, but just look from the integral on. What does that look like? Looks like another equation we saw just a little while ago. What does that look like the equation of? Work. Looks like the equation we had for work. The integral of force with respect to position from position 1 to position 2. But notice the only difference with this is that there's a what with it? Negative. So a change in potential energy can be found generically with a force and a displacement by finding the negative work done. A change in potential energy is equal to the negative work done. Now, this is the way it's written in your text. I think on your reference table, if I move this around, algebra, do the algebra on this and solve it for vector F. What do you get? Can you tell me? What is F equal to? Solve it for F. What do you get? What do you get? Almost. That's solved for negative F. Solve it for F. Negative du over ds. In other words, a force is equal to the negative derivative of potential energy with respect to, what does S stand for? Position. Okay, it can be any position letter. X, Y, S, R. You pick a letter, put it in there. Just know it means position. Okay. All right. If you wanted to find gravitational potential energy in a gravitational field, like close to a mass, once we deal with like planets far, 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 far away from one another, we would not do this. This only deals with masses close to each other. So the change in the potential energy, which is U minus U0, would equal mgy. We didn't use y last year. What letter did we use? mg delta h. Okay, it's y. It's a vertical distance. Okay, where U0 represents the amount of potential energy at some y value of 0. It's your reference energy. Figure out what your reference level is. Usually it's most convenient to say that U0 is 0 somewhere, the lowest point in the question. Consider that to be where there is no potential energy, the lowest point. It doesn't have to be the ground, okay, because these are relative amounts. Choose U to be 0 at any convenient reference point, the lowest point in the problem. That's my hint to you. Always use the lowest point in the problem as your reference point. And keep in mind that when objects attract each other, the further apart, the more potential energy they have. All right, let's think about that for a minute. Here's a mass. There's another mass, the Earth. This pen has a certain amount of potential energy right now, yes? If I were to move it here, without hurting my foot, I'd stand on one leg to do this, so I don't hurt my foot, which has got a broken bone in the ball of my foot. Hold it up here instead. I moved it higher up, right? Talk to me about how much potential energy it has here compared to here. It has more here, right? It's further away from the Earth. The further apart things are, the more potential energy they have. Think of that example to help you. All right, elastic potential energy. First of all, remember that if springs are ideal, they obey Hooke's law. Fs is minus kx. The minus just means opposite. The force on the spring is opposite the way you stretched or compressed it. We saw that equation in an earlier chapter. I believe we saw it in chapter 4. Now let's talk, and of course, elastic potential energy would refer to the stored energy in an elastic system. Things are stretching. It doesn't have to be a spring, as long as things stretch. Now we're not using a PE again. We're using a U. But we are going to add subscripts. So this type of elastic energy, elastic potential energy, would be US. Gravitational potential energy is UG. Keep the subscripts to help you know which type of potential energy you're referring to. And that only works, that equation for elastic potential energy only works if the spring obeys Hooke's law. It's ideal. It's an ideal spring. That's the language you're going to see in a question. It's an ideal spring. Ideal spring means it obeys Hooke's law. If it doesn't, you can't do that. To find the potential energy, you have to use the integral, the negative integral of the force with respect to position. And X, of course, in that equation refers to an equilibrium position where it's not stretched or compressed. So if you have a general conservative force, the force is negative du, that says dx, whatever the position is. And this should make sense too. That's Newton's first law. When is something in equilibrium? When the net force on it is 0. Okay. If the net force is 0, that brings us to different types of potential energy functions we might see. Graphing potential energy versus position. And here's where I think you'll see why we use a U. Ready for the first graph? If you get a graph, see, there's the U. If you get a graph of potential energy versus position, which is concave up, you know what concavity refers to, right? Opens up. This refers to a type of equilibrium known as stable equilibrium. There are 3 types of equilibrium you need to know about and recognize. Stable equilibrium refers to an object, which is an equilibrium. Move it away from its equilibrium position a little bit, and what does it do? It goes right back to its normal equilibrium position. It accelerates right back to its equilibrium position. I'm going to give you an example. Imagine a pendulum bob. I displace it a little bit. What does it do? It tries to go right back to its equilibrium position hanging straight down. That would be stable equilibrium. Stable equilibrium on a potential energy versus position graph is concave up. Can I go to the next one? Unstable equilibrium. Don't worry, if you missed this, the slides are in your Google Classroom now. They were posted this morning. You can go to the PowerPoint, look at it later. Here's our unstable equilibrium graph. Notice that this graph is concave down. What does it mean when we say something is unstable in an equilibrium position that's unstable? It means that if you displace it a little bit from where it's in equilibrium, it accelerates further away from the equilibrium. Let me give you an example of where that might happen. Think of like an 18-wheeler tractor trailer. Equilibrium is when the trailer is oriented, all the tires on the ground. It rounds a turn maybe a little too fast, and what does it do? Starts to tip away from equilibrium. What's it going to do? Is it going to go back, right itself back up? Usually not. It accelerates away from its equilibrium. A toddler learning how to walk, standing up. A toddler is unstable on its feet, right? Don't be nasty, but I did this to my daughter when she was little. I didn't want her to walk because the minute she walked, I know they go right to running. And now I got to keep my eye on her all the time. She's going to get into trouble. So I knocked her down all the time. I just would touch her and boom, she'd fall over. Okay, that's what they do. Toddlers on their feet are unstable. Okay, unstable equilibrium. Now there is a third type. This is neither concave up or down. So this is called neutral equilibrium when I graph potential energy versus position. Neither concave up nor concave down, which means that if I have something in an equilibrium position and I displace it, it just goes to a new equilibrium. Let me give you an example. This pen, that's an equilibrium right now, isn't it? I'm going to push it. Is that an equilibrium now? That's neutral equilibrium. I pushed it away from its equilibrium, but it went to a new equilibrium. That's neutral equilibrium. Now, that's it. Let me talk to you about, on these curves, if you're at a minimum on the curve, that would mean your force is 0, right? Equilibrium means your force is 0. And the system is stable. So if you happen to be at a minimum, at a max, if the force is 0, obviously, then you're unstable. And conservative forces always try to put you towards a position of lower potential energy, like gravity, right? Gravity, what does it do with this pen? I release it, makes it go towards a lower potential energy position. Gravity is conservative. Hold on, one last thing. You learn in calculus how to evaluate for points of inflection on graphs with concavity. Do you remember how you do that? Second derivatives. You're going to be doing second derivatives of potential energy functions, plugging in a position. If you get a positive result, it would mean you're in stable equilibrium, concave up. If you get a negative result when you evaluate it, it means you're concave down, unstable equilibrium. If you get a value of 0, what would that mean? Neutral equilibrium. Very good. All right, have a great weekend, everybody.